Equation mx double dot if not cosine omega t or sine omega t, or in general what we are doing, we are studying the problem x hat, let us say dot omega t and x equal to real part of. So that is our procedure. We are making the equation kind of complex, and then knowing that the real solution will be real part of the complex solution we get, that is x hat. Now, if you follow yesterday's discussion, then xt, this was equal to f naught divided by m under root omega n square minus square plus twice zeta omega t square and e to the power j. Yes. Any problem? Where tan phi 2 zeta omega n divided by omega n square minus omega square. So this is what we got. The x hat t, this is equal to f naught divided by m, this quantity, plus of course a cosine omega t minus, let us say, phi naught, omega nt minus omega dt minus phi naught, and e to the power minus omega n zeta omega nt, and this part is the part which is due to the initial condition of the system. So the entire initial condition is absorbed in the second component. The first part is actually the steady state response, which shows that even if this dies down, but still in the steady state part, that is when t is very large, then this kind of I'm not sure whether this is very much visible or not. Let me just check. So this part together with this one, that is actually giving us the steady state response. So if you consider the response, so what you will get is like this. There will be a steady state part, and this part, this will be something like this, it will be like that, but then eventually this will come. So this part is the transient part. And beyond this one, this is the steady state part. Now, steady state response is the most important part of this because this will persist. Okay, so the transient part will die down because every system will have some amount of damping, even if it's very small. So there will be some amount of damping present in the system. So the transient part will be there. Of course, it may have a large amplitude. I mean, the response may be very large at one time, but it doesn't matter because it will be transient. It will go away, but this one will actually persist. Okay, so whatever effect we get from vibration, mostly this is due to the steady state response part. So we'll consider the steady state response in somewhat details. Let me write down clearly the steady state response. So now I'll consider x steady state, and this will be equal to f naught divided by m under root omega n square minus omega square 2 zeta omega omega n square, and this is e to the power j omega t minus phi, where tan phi equal to 2 zeta omega omega n divided by omega n square minus omega square. This part we actually derived in last class. Now, we would like to actually modify this first expression a little bit. So what we'll do, we'll take out this omega n square. So here I'll take out omega n square. Okay. So 1 omega n square and this will be omega n square like this, and here omega n square will come. And so I am rewriting the expression x excess t this way. Now what is this one? Then let me check. X excess t, this will be equal to f divided by what is m omega n square. You know k equal to omega n square equal to k by m. So m omega n square will be equal to k. So I can write down this as k, and the other part will be 1 minus, I will define omega by omega n as a ratio. This is r square, I'll name this one. Omega n will cancel, so again omega by omega n will be there. So 2 zeta r square e to the power j omega t minus phi, where tan phi, again if you divide by omega n square, both numerator and denominator, then this will be omega n square. This is omega n square. So 1 omega n will cut away. So 2 zeta r divided by 1 minus r square, where r equal to omega by omega n. So this is the, we call the frequency ratio. Let us say we'll call it a frequency ratio. Now we have a very interesting thing, that is f by k is appearing, and there is a factor over there. So what is f by k? How do we interpret this f by k? Why do you think I have written this expression this way? If you see, if you have yeah,
static displacement.
right. So if you have a let us say spring mass damper system, and I apply a static force, let us say F naught here. So there will be a displacement, right? And in this displacement is a static displacement. So x static, it will move by an amount x static, and that will be equal to F naught by k. This damper will not contribute anything because it is static. Damper will contribute when there is a motion. So this is the equilibrium displacement of the equilibrium, I mean the displacement at the equilibrium position when a constant force F naught is applied. So what we see here, that here x excess, now this one is the static displacement, but now it is multiplied by a factor. So let me write it down again. So xs, x stat, this one will be equal to x static, which is equal to f by k times a factor f and e to the power j omega t minus phi. So this factor, this is kind of a magnification factor. So what is happening, because of the existence of a frequency in the forcing, so the steady state amplitude, this is the amplitude part of the steady state response, the amplitude is actually magnified with a magnification factor f. So this factor will be 1 divided by 1 minus r square plus twice zeta r square. So this is the magnification factor. And of course there will be a phase difference phi. Phase difference will be tan phi. This is equal to 2 zeta r divided by 1 minus r square. So this is the magnification, and this is the this is the phase. I'll show. I mean, this why I have written minus pi. It will be a little bit. It will be clear there. Of course, from a mathematical point of view, it was very obvious. But now we'll consider this one a little bit in a detail. So what I will write down now is that this f. Let me draw this f with respect to r. So r, that is equal to omega by omega n, and this multiplication factor. So when r is equal to 1, r is equal to 0, f equal to 1. That is obvious because 0 forcing, omega is 0, the r is 0 means omega is 0, and that means that the frequency is 0. That means the time period of the forcing is 0. That means it is a static force. So it starts from 1. You can see f equal to 1, and then when r tends to infinity, then what happens? This term r tending to infinity. So yes, so r tending to infinity, again, what is going to happen? That f will be tending to, what is going to happen? R square will be much large compared to 1, so therefore it will be r to the power 4. R to the power 4 plus certain terms r square. So this is again very less compared to r to the power 4, so what remains is the r to the power 4, and then this will be 1 by r square. So it will decay like in 1 by r square. Okay. This form it will decay. Now, interesting thing will happen near r equal to 1. So what happened? At r equal to 1, f will be equal to 1 divided by 2 zeta and r. So 1 by 2 zeta. So now you see one thing, at r equal to 1, it will have a peak something like this. So let me draw it more clearly. So that is for zeta. And now if so, this is 1 and it is decaying. Now if you have more amount of zeta, so if the zeta increases, then this peak will be like this, like this. If zeta is equal to 0, then what will happen? This magnification factor, if zeta is not equal to 0, then 1 by 2 zeta. So now you see the part is 2 zeta is the part, and if you have zeta increasing, so what we see here from this graph, if you draw this graph, two things will be there. One is that when the zeta is increases, then the peak of the this magnification factor, this decreases. Okay, that means actually what will happen, at r equal to 1, which corresponds to resonance for undamped system. Now for the damping, what will happen? The magnitude of the amplitude, that means the amplitude will be limited to extent 1 by 2 zeta. If the zeta value increases, then the response, the amplitude of the response at resonance will go down. At the same time, we see that this curve is actually becoming more and more flat. Okay, when zeta is increasing. So two things we are noting, that the zeta value is decreasing, zeta value is increasing, so the curve is actually its maximum value is going down, and at the same time it is becoming broader and broader. Okay, so there is a broadening effect because of the damping. The damping coefficient increases, so therefore it becomes more and more flat. Okay, so that is one
Excuse me,
thing.
sir.
Yeah.
Sir, actually, the peak of the peak will shift towards left, right?
Yes.
With increasing damping, the peak will shift towards the left, right?
That will shift towards left, but that, okay, I'll talk about this thing.
Okay.
That what is there is that the what immediately we see that the peak is going down and it is becoming flat. Okay. Now you can check that what is the value of the frequency where. So I want to find out what is the value of R where f is maximum. So where f6 maximum. So this is what we want to get. So it means that when f is maximum, that means this 1 minus r square plus twice zeta r square, that has to be minimum because this is appearing directly in the denominator. So ddr of this will be equal to 0, and this gives us this gives us 2 say minus 2 times 2r 1 minus r square plus.
Sir, is it not f is equal to 1 by f 1 by root over 1 minus r square a plus 2 xi r in r square?
I'm not getting it. Yes, what? What's
Sir,
that?
why you jump a step in the derivative in first line? Is it?
Here.
Okay,
Okay.
okay.
You take derivative. So 2 1 minus r square minus 2r, right? Plus 4 zeta square times 2r, that is equal to 0. That's it. It's not clear.
Yes,
Okay.
sir.
Okay, good. Now it will have two roots. One is r, and another is, let us say, 4r. So minus 1 minus r square plus 2 zeta square. This is equal to 0. So we'll have two roots. One is r equal to 0. And at r equal to 0, you see that this is actually a minimum. It is not maximum, it is a minimum. And the maximum will happen when r equal to, let's say, 1 minus 2 zeta square. So these are the two roots of this equation. I am taking the positive root only. So here you see the peak actually, as someone was pointing out, that the peak is also shifting towards left. So if you draw it more accurately, so what you get is that at one, so like this, okay, peak is a little bit left, okay, peak is at 1 minus 2 zeta square. When zeta is increasing, so peak will shift a little bit left here, and at the same time it will become somewhat a little broader and broader. So it will become flat and flat, flatter and flatter, right? Like that.
Constraint on zeta, right? Like zeta should be less than half.
Beta?
1 by root 2. Like there's a constraint on zeta, like r should be real, right? So the square root under the square root should be positive.
Okay. No. R is always a real number. So I am discarding the imaginary part. R cannot be imaginary.
No, sir. Like if zeta is supposed to, then like there will be no maximum, right? Like not for all values of zeta we have a real r.
Of course. There is, if zeta, this is only true for zeta less than 1 by root, greater than 1, less than 1 by root 2. If zeta is more than 1 by root 2, then of course what will happen? The peak will be like this. So there is only single peak. Okay, like this. So this is the case when zeta equal to 1 by 2 zeta square 1 by root 2. Beyond that, actually, there will be, there is no such no such peak, but it will gradually fall down. So therefore, r equal to 0, so it will start falling down when beyond zeta equal to 1 by root 2. Okay, so people sometimes, have the conception that, well, zeta is more than 1. If we ask them to find out what will be the steady state, they actually say that it will go to 0 because they have the idea of only the free vibration. But in the forced response, it will not go to 0. It will be very small, but it will never go to 0 when zeta is more than 1. So of course it depends upon the value of the R, but it is not true that for overdamped system there will be no vibration. So if there is a forcing, periodic forcing, then there will be, of course, a vibration even for the overdamped system. But the thing is that this magnitude of the amplitude will be very, very small in that case. Now that is what we are saying. The peak is actually shifting towards left. Okay. And it is its magnitude, the maximum value at R equal to 1. So the maximum value, you can check that, you can find out what will be the maximum value if you just put, let me put that way, that at R equal to 1, its value is this one, but its maximum value is a little bit more than 1 by 2 zeta. So let me find out what is the maximum value. So F max. F max will be equal to 1 divided by 1 minus R square, that is 1 minus 2 zeta square minus R square plus 4 zeta square 1 minus 2 zeta square. So F max will be equal to, again we are considering only the case zeta less than 1 by root 2. If zeta is greater than 1 by root 2, then the maximum value is at 1. So otherwise it's good, it goes up. So you can see that this will be equal to now 4 zeta square. So this becomes 4 zeta to the power 4 minus plus 4 zeta square minus 8 zeta to the power 4. So actually 4 zeta square minus 4 zeta to the power 4. So this will be equal to 2 zeta 1 minus zeta square. So that will be the F max value. This is the F max value. All right. So that what we get is that the maximum value of this one will be equal to, this is F max, which will be equal to 1 by 2 zeta under root 1 by 1 minus zeta square. Again, another thing it is seen now that if the value of the zeta is increasing, it is becoming broader and broader. That you can say that it is becoming broader and broader in the sense that we want to find out when the amplitude actually becomes 1 by root 2 of F max. So now my question is, why I am doing this is that, suppose I have a curve. Right? So this is F max. And this is the value of, let us say, R star, where this is maximum. Okay. Now we may be interested in finding out where is these two frequencies R1 and R2, where this is F max divided by root 2. Now why root 2? Root 2 because this is called a half power bandwidth, this difference between R1 and R2. Why? Because the power depends upon the amplitude square. Okay, power is energy will be half the potential energy half kx square, for example. Kinetic energy will be half m x dot square. Everywhere you'll get, if it is x dot square x square, so this is x hat square, and this will be omega square x hat square, and so on. So everywhere you will get the square of the amplitude in the energy term. So also in the power term you will get the square of amplitude. So square of amplitude, actually the power. So if power is actually reduced, so what it means that I want to find out that bandwidth beyond which the total energy of the system actually falls below half its value. So this is the part, that means the amplitude is actually falling down by √2. So the power or the energy dissipated per cycle or energy content in the cycle, they will actually also fall down by a factor half. So I am interested in find out this is what is the value of R2 minus R1. Okay, R2 minus R1, that is delta R. What is the value of this delta R? So what I want is that I want to find out what is the value of zeta. So this will be 1 by, my question is 1 by √2 times 2 zeta 1 minus zeta square, and this is equal to 1 by, I want to find out this one, that is 1 minus r square plus twice zeta r whole square this one. I want to first get the root of this equation and find out the difference between these two roots. So this task is actually kind of a kind of algebra which I would suggest you should better do. I'm just giving you a kind of introduction to this. So 4 zeta square r square, this is equal to 2 times 4 zeta square 1 minus zeta square. So I have here, so r to the power 4 minus r square will be r square is 2r square, so therefore 1 minus 2 zeta square 2r square, this is 1 minus 2 zeta square plus 1 minus 8 zeta square 1 minus zeta square equal to 0. So what we'll do, we'll get the value, the two roots r1 square and r2 square from here, and from that we have to find out r2 minus r1. Okay, r2 minus r1, so we have to find out that. So this is actually, you can take this task, you can find out this problem, but I'll just simplify the system a little bit and see what we'll get out of this. So this is the exact solution. You can find out R1 and R2 and find out this difference. But I'll take a little bit, I'll simplify this matter a little bit. So what I'll assume, so this I leave it to you how to carry out this R1, R2 minus R1, how to get that, the difference between the two amplitudes, two frequencies where the amplitude will fall down to 1 by √2 of this value. But I will take a small shortcut here. So I will assume that zeta is very, very small compared to 1, because that is what is most important. So I'll consider the case when zeta is very, very small compared to 1. When zeta is not that small compared to 1, then of course you need the exact analysis. But when zeta is very, very small compared to 1, then we can see that we have, let us say, F max is 1 by 2 zeta 1 minus zeta square. Is this correct? Is this correct? I wrote?
Yes, sir.
Yes, yes.
Okay, so these amounts, these actually, because zeta is very small compared to 1, so therefore this term is negligible, and the maximum value will become 1 by 2 zeta. Okay, 1 by 2 zeta. Then my task is to find out √2 times 2 zeta equal to 1 divided by under root 1 minus r square plus 2 zeta r square. So this will become 1 minus, so 1 minus 2r square plus r to the power 4 plus 4r square zeta square minus 4r square zeta square minus 2 times 4 8 zeta square. Okay, 8 zeta square, this is equal to 0. Again, what we see is that so this becomes equal to r to the power 4 minus r to the power 4 plus 4 plus 2r square zeta square minus 1, right? Okay, zeta square, 2 zeta square minus 1, and this equal to this plus 1 minus 8 zeta square, that is equal to 0. Okay. All right. Now what we get out of this? So okay. So here you see so what do we do out of that thing? This is 4 zeta square now after that so it becomes 1, so f max is going down by root 2, so that is what we are getting. And what we can do is that so at r tending to, now one more thing will be there, because this will happen and that will happen at r equal to 1, because this is equal to r 1 by r equal to 1 minus 2 zeta square, so that will be approximately equal to r. So this star will be approximately equal to 1. So r is actually very near to 1. Near to 1, so that effect we can see. R is let's say so let me do a little bit thing. So I'll consider R equal to, I'm just considering because this is, so this is R equal to 1. I am considering the value very near to R equal to 1. So R equal to 1 plus, let us say, epsilon. I am considering R equal to 1 plus epsilon. So in that case, R square, so F will be equal to, F in this case, this will be equal to 1 divided by 1 minus R square, this will be equal to 1. So R square will be equal to 1 plus 2 epsilon plus epsilon square, and epsilon square I neglect because this is very small compared to the other terms, so I am neglecting every time this epsilon square over there. So R is like that. So 1 minus r squared, this will be equal to 4 epsilon squared. 4 epsilon squared, it will be 2 epsilon, and 4 zeta square r square. So there will be 4 zeta square r square equal to 1 plus 2 epsilon. And since epsilon and zeta is also small, epsilon is also small, so therefore this term can be actually dropped out. So what we get from here is that f will be approximately equal to 1 divided by 2 under root epsilon square plus zeta square. So if you just scale it, so therefore what it is showing that if you take, say, epsilon equal to 0 is here, so if you plot this here, this curve will be actually very smooth curve. Okay, and in this case, actually, when epsilon equal to 0, this becomes equal to 1 by 2 zeta. Epsilon equal to 0, you can say that 1 by 2 is 2 zeta. At the same time, you see that this curve, you see f square. Now consider f square, so there will go 1 by 4 square plus 1 square. So this curve is actually kind of proportional to the power. So now you see that if you want to consider epsilon, where this will go to 1 by root 2 value, that means f will go to 1 by root 2 zeta, that means 1 by 2, f maximum is 1 by 2, so therefore this will be 1 by root 2 times 2 zeta square is 1 by 4 epsilon square plus zeta square. So one can check here, let us say that 4 epsilon square plus 4 zeta square equal to here 8 zeta square. So epsilon square will be equal to zeta square. So now you see one thing is that epsilon, so epsilon will be equal to plus minus zeta. So here at plus minus zeta, so what I am doing, said zeta and minus zeta, this curve is actually going down to its value 1 by root 2 times f max. So now you see one thing here, that in this particular scenario, what you see that this the difference between these two values, that is now R1 is actually here, R1 will be equal to 1 minus zeta approximately, and R2 will be equal to 1 plus zeta. So R1 minus R2, R2 minus R1, in that case you can see that R2 minus R1 will be approximately equal to 2 zeta. So now you see from this simplified analysis, so what was the simplification? I inflated the curve around r equal to 1, because when zeta is very small, the value of the frequency factor where f becomes maximum is approximately equal to 1 if you neglect the higher order terms of zeta, then zeta square. So and the maximum value is 1 by 2 zeta. Now when it goes to 1 by root 2 of its value, then you can check that epsilon in that particular approximation, it comes to plus minus zeta. So the bandwidth, that means the difference between these two, the maximum frequency and the minimum frequency over there, this becomes equal to 2 zeta. So now you see one thing, that whenever we are increasing, so what are the effects of our increasing damping? So with increasing damping, first of all is that amplitude. So increasing damping, f actually decreases, f max decreases. Second is that the half power bandwidth, that is, this is, let us say this half, let's say delta R half, this actually goes up, and of course, so this is what we have seen with this simplified analysis. But if you want to do exact analysis, it will be, you can try that, you will get the similar thing, but it is not so important, because for large amount of damping, we do not have to bother too much about all these things. It is only useful for small amount of damping. So that is what we are doing. So that the F max is going down and it is actually broadening. Okay, so it becomes that when zeta is increased, what will happen? That this will become actually like this. The curve will become like this. So if you increase the value of this, so it will become flatter and flatter. But again, with the approximation, that is, we neglected the higher order terms of epsilon here. That means we are always considering very near to our resonance condition, where zeta is equal, when zeta is equal to 0. So near about that, we are just increasing the zeta a little bit and seeing what is going to happen to the that frequency response function F. Okay. I think now we have got a kind of a broader picture and of what is going to happen to F. So at R equal to 1, for a very small amount of damping, which we need like this. If you increase the value of the damping, this will become like that. This and so on. So this is the value F. Okay. So and this goes from 1. So it is increasing. Right? Now, one interesting thing. Now, what is so? This is the F part, and what is going to happen to phi? R, and now I have to say what is going to happen to this phi. You see, tan phi will be equal to 2 zeta R divided by 1 minus R square. So when R equal to 0, of course, phi starts from there. When R equal to 1, this becomes infinite, so therefore this will go to 90 degree, pi by 2. When R more than 1, then actually tan phi becomes negative because it becomes more than 90 degree. When R tends to infinity, then what is going to happen? This tends to 1 by, this equals to 2 zeta R divided by R square, and that becomes minus 2 zeta by 2 zeta by R. So again, you see, as R becomes large and large, it is going to again, this becomes minus, so this becomes 0, but with a negative sign, because this term is actually negative. So what we will get, so it reaches this pi when R tends to 0. So what will happen is that the response will be like this. Okay. When zeta is equal to 0, we show an abrupt change. So this is equal to zeta equal to 0. As zeta is increasing, like this. Okay. And similarly, like that, and maybe like this. Okay. So this is what will happen if you increase the value of zeta. So now you see that phase is changing from positive, when there's a difference between R equal to 1, the R less than 1 and R greater than 1. In R less than 1, what we see? We see that the phase difference becomes less than pi by 2, and beyond that R greater than 1, phase difference is greater than pi by 2. Please remember this part. I will use this particular fact later on when we study the hysteresis involved in this particular situation. So this is one way to show that this can be shown. I mean, this is one way to show the response, the steady state response, accepting the factor f I have taken. Actually, the response will be x static times f. Okay. So this is the response, the steady amplitude, and we have the phase. So this amplitude and phase constitute what is known as the Bode plot. But this is actually, I am drawn in the linear scale. Bode plots are normally drawn in the logarithmic scale. So this is one way to show that. Okay. Is there any doubt? Is there any doubt so far? Okay. So now we'll move to one more situation. Now let us consider what is the power flow. What is the power flow? Okay. Now you see, you have the equation mx double dot plus ax plus cx dot equal to f naught cosine omega t. This is what we have. And then if I multiply this by x dot throughout, so this becomes equal to mx. So this becomes, you see, ddt of half mx dot square plus ddt of ax square. Okay, half kx square. Check that, plus cx dot square. This is equal to f naught x dot cosine omega t, and this is the force part, and this is the this part. Okay. Now what we see from this is that, what is this one? What is this? This is the power given by the external source to the system. And now, if we take, let us say, if we integrate over time, so that now what I am doing, I am integrating this equation ddt of half mx dot square plus half ax square ddt, okay, plus cx dot square dt, and now what? This is 0 to 2 pi by omega. That means in one time period. So what you see, what I want is, suppose there is a steady state is going on, I am considering only one time period. So this is the steady state. Okay, steady state. Transient is now gone. The steady state, we have this time period t equal to 2 pi by omega. So I am considering this integral over this particular time period. So this is what, and we have now f naught cosine omega t x dot dt. Okay, that's it. Now one thing here, you see, this becomes actually ddt actually goes away, so therefore this becomes differential of that. Now what is this? What is this integration? What is the value of the integration? If you integrate, what will be the value? You see, this integral, this will vanish because, means integration will vanish because this will be half mx square plus half kx square at x equal to, let us say, at t equal to 2 pi by omega minus half this same thing at t equal to 0. So if you start t from here, so this is the difference between these two things at time t equal to 0 and t equal to 2 pi. But because this is periodic, so entire thing will be same because they will repeat after one period. So because of the periodicity, actually this will go to 0. And then you see now what we have left. is that the Cx dot square dt, this is 0 to 2 pi by omega, this is nothing but your 0 to 2 pi by omega, and then f is that f x dot dt. I'll say that right down f, just to say that this f is equal to f naught cosine omega t. Now you see one thing is there, that is over a time period, what is going to happen? Over a time period, earlier case what was happening when c equal to 0? Over this time period, there was no net inflow of energy from the source, because a part of the cycle energy is being drawn from the source, and the other remaining part of the cycle energy is being thrown into the source. So therefore, overall, over the entire time span, over the entire time period, there was no net change in the energy from the source. But now that does not happen, because this term is positive. This term is always positive, right? This term is always positive. Okay. And then if this is the positive value, then what is say that ft, so now we are considering steady state motion. So x dot will be equal to, let us say, x static times f minus omega, okay, sine omega t minus phi. So that is x dot. So therefore, this integral 0 to 2 pi by omega, this will be equal to x static, but it's not by f naught by k times f, okay, times minus omega. So therefore, this is minus omega cosine omega t sine omega t minus phi dt. Now you see one thing here, this becomes actually 0 to 2 pi by omega. I am not much bothered about this part, that is f naught by k times f times omega with a negative sign. So this becomes equal to cosine omega t sine phi, cosine sine omega t cosine phi, and cosine omega t because of the negative time, cosine square omega t sine phi, and minus sine omega t cosine omega t and cosine phi, right? So this dt. You now see one thing, that this you see integral sine omega t cosine omega t 0 to 2 pi by omega, this becomes 0. Okay, that you can already establish. This part is actually, so therefore the integration of this part, this will be equal to 0 to 2 pi by omega f naught by k f omega and sine phi, so therefore cosine square omega t sine phi dt. If you integrate, this becomes equal to pi by omega, right? Half and pi by omega. So this is the value of this integration. Now omega cancel out. So therefore we have here f naught by k, f and x static. So this is what we have. I did not consider x squared. So sorry. So there was one term x static. So now f naught will come. So f square I missed somehow. Okay. So this is part which we are getting. Now we have just let me write down. So therefore this becomes cx dot square dt 0 to 2 pi by omega equal to pi f naught square by k, and this times sine pi. So now you see one thing, that is the left hand side of this integral. This is actually a positive quantity. So integrand is positive, so therefore this is always positive. So that means that also positive. That means phi has to be, sine phi will be positive, and that means phi has to lie between 0 to pi. Okay, and that's exactly we have seen in our case, that is the phi value is actually lying between 0 to pi. So that is in order because the energy is being dissipated over there, and the same amount of energy is being supplied by the source. Okay, this is the kind of energy balance we are seeing, that the energy is actually dissipated over cycle and energy being supplied by the force. Now let us see what is the implication of this part. You see the energy. So the energy dissipated is equal to half Cx per cycle, half Cx square, and this is dt 0 to 2 pi by omega. Not half, this is this part, and that has to be supplied. Okay, and what is the supply energy per cycle? Supply energy, what will be the supply energy per cycle? The supply energy will be equal to, what will be that? The supply energy will be Ft x dot t dt 0 to 2 pi by omega. Let me see one thing. This part is actually, you can write down 0 to 2 pi by omega and Ft, because x dot t is nothing but dx dt. So therefore this becomes dx t. Okay. Now what we see from here is that this energy, now we can visualize that. So energy dissipation is positive quantity here, and this has to be kind of, and this is the total energy dissipation, because it's the energy supplied energy per cycle, and that must be equal to the dissipated energy. So therefore this is the amount of the dissipated energy as well. So supply energy is equal to dissipated energy. So this is the dissipated energy. But now can you see the implication of this? If you draw a curve, let us say, if you draw Ft versus Xt, okay, Ft versus Xt, then you will see that this curve will have a closed curve. So therefore this curve will be something like this. That may have some other shape, I don't care. But what is it saying? That the energy, the integral, that means the area under this closed curve, must be equal to the energy dissipation, and that is equal to Cx dot square dt and 0 to 2 pi by omega. So now you see that in the Fx, so force and displacement plane, it will look like a kind of a closed curve, and the area under the closed curve will be numerically equal to the energy dissipated per cycle. So this kind of closed curve is called the hysteresis curve, because there is a kind of hysteresis. I'll explain in the next class. But I hope that except the mathematical part, which at sometimes I was very fast, but you have understood the physical concept behind what is happening if you have a damping. So this is very important, because we need to know the effect of the damping very clearly. Why? First of all, in the analysis part, this is required, and second, our objective most of the time will be to reduce the effect of reduce the vibration. And in order to reduce the vibration, sometimes we have to increase the damping. But we have to be very sure whether the increase of the damping, what is the effect of the damping? First of all, we have to have a very clear idea. Then and only then we'll be able to play around with the damping part. Okay, so in the next class, I will discuss about the hysteresis, and things will become more and more clear as we proceed. Okay. Today's class, do you have any question? Any question, please? Okay, on Friday, on Thursday, we are having a class test. Okay, so this is known to you, all of you. On Thursday, we'll take a class test. Okay, and somehow this extra class concept did not work last week because a lot of work is going on in JE office, so I could not take out time. I'll let you know when to take the extra classes, but definitely 4 classes are due, and I'd like to compensate in due course. Okay, I'll let you know when to take that class. Okay, so any other question? Yes, yes.
Like, what is the syllabus for the
Question
class?
will-
Oh, syllabus will be up to the undamped oscillation. Damping part I could not complete, so therefore I don't want you to break your head on that. So undamped oscillation, including the how to derive the equations of motion and so on. Okay.
Okay.
Sir, you will give the all question are numerical or
No,
is there any?
questions, not numerical, but there is no theory question. There should not be any theory question. I'll ask you to solve. They'll be all problem based.
Okay, sir.
Okay. All questions will be problem based.
And should I done all the problem of SSRAO? For class test?
At least you should be clear of how to. You need not solve all the problem, but you should know how to solve these problems. Okay.
Okay, sir.
It should not look very new to you during the examination. That's what I expect.
Okay.
Okay. ठीक. Okay. Any other doubt? Okay. So if it is not there, then let us now stop today. We are again meeting on.
Okay, sir.
Yes. Papai.
Sir, you have said that if damping is consume energy, then what will be the procedure for reducing vibration?
Damping.
Yeah.
Damping. Yes.
If damping the deficit the energy,
No energy. Yes. Damping will reduce the energy of the system, right?
and or then what will be the procedure of reducing vibration?
No, sometimes we have to increase the damping, sometimes we have to decrease the damping, because always increasing the damping may not be a good idea. Those who are studying vibration control, maybe you have taken that course, some of you, they will learn about it. That is, in certain frequency range, the increasing damping will give you
Sir,
actually.
mass dominated, damping dominated, and stiffness dominated, and vibration isolation process. That's all.
Yeah, in vibration isolation, in the high frequency excitation, the damping is not very effective for isolation.
Okay, sir.
Okay.
Okay.
So definitely it must have been taught in your vibration course, vibration isolation and control. Are you taking that course, Papai?
Yes, sir. Yes.
Okay, so then it must have been taught there.
Okay.
Okay, take it. Any other? Okay. Let me now close then the session. Thank you.
Thank you.